Okay, greetings everyone. How are we going to get the most value out of IT in the future? We can try to ask this question both as designers and as users. One answer for an engineer would be to maximize the reliability and availability of the technology in the cloud or at the edge, because those dynamic aspects are at the root of what enables a service to take place. But we also have to remember the purpose of the service. What function should a service offer and in what context? Is it shopping? Is it a search directory, perhaps an online map, authentication service, office productivity tools, and so on? The first part is a dynamical or operational answer. The second is a semantic or a functional answer. Then there's a third issue, which is less popular. It's a question of maintenance. How can we manage all of the pieces, keep them running? This is an expensive piece of the puzzle because it often involves human judgment, even human attention, human work. So this is where assisting automation can help. Even better, autonomy or self-determination can be a key strategy in designing tech. Even after 30 years of internet, we still struggle with just a few basic issues in our approach to this because we use methods designed for a slower, more static age, old-fashioned data models, old-fashioned approaches. And of course, we keep redefining the goalposts for success. We want greater speed, greater scale, greater scope, even greater mobility. There's one technical issue in particular when designing services that's important, and that's managing causality, preserving the order of cause and effect, which is essential to ensure the accuracy of transactions. For example, when writing data from financial transactions or contract payments, even fault findings, fault diagnosis when monitoring systems, or preserving the order in machine learning training. And then later when we come to search for the results of that learning, we want to make sure that we replay things in the correct order, no matter who is watching and where they are. This is a relativity issue. So what I'd like to sketch out here is how we can form a unified approach to these issues based on something called promise theory. And this is something we've already been applying together with research to design both the dynamics and semantics of hardware and software components. The result is a kind of a knowledge-oriented approach to the design of autonomous networks. And in particular, if we follow something called the Semantic Spacetime model, which is an application of promise theory, we can ensure that agents keep clear promises, and so they remain trustworthy and safe in a predictable way. So here's a quick overview of what I want to cover. First, I want to talk a little bit about the challenges of modeling autonomous processes in an ambient environment, Then briefly introduce, without too many details, promise theory and semantic spacetime. Comment on some past examples that have used these approaches, and then ask, what should these autonomous networks look like in the future? How do we need to build these things? How do we put self-sufficient processes into the real world? So let's imagine a world of autonomous agents, where agents can be humans, hardware devices, software running on some network computer, anything, hardware or software. And both the providers and the users, the clients, can be agents. That everything is an agent. So what do we mean by autonomous agent? Well, autonomy is the ability to act independently, locally, within some context, and then to make decisions about it. The answer to this is actually closely connected with ideas about space and time, because if you're autonomous, if you're alone or independent, You're not connected with things around you. So it's about how close you are relative to others, or how closely connected you are. More concretely, autonomy is a policy to coordinate less with other agents, to communicate less. It reduces dependencies, communication, and therefore latency. And so it saves energy and time, but it also potentially makes agents less vulnerable to external influences in a security sense. So autonomy has many kind of advantages. And this, we shouldn't think of this as making agents sort of like robots that can think for themselves. Rather, it's about making systems that can choose from decisions that have already been made by humans. So the ability to act independently is a scale-dependent concept. If we look at this picture, we see drones and buildings and cities, and we can say that the drone is independent if this acts independently, or a building is independent, or a room in the building is independent, or a collection of buildings may want to cooperate to share power. They can operate independently from another group of buildings. So we can always draw a ring around a particular region of space and time and call this an autonomous agent. So the question then becomes, at what scale in space and time do we want to claim autonomy or independence? We need to model this scenario, and the world has a lot of variables that we don't control. Variables need a schema or a representation, and they need some processes, some information technology to process it. This is more straightforward when agents stand alone, but when agents need to coordinate or share information, then they need to cooperate, which may require common data formats, shared data stores, databases, and so on. And this adds to the complexity of the system through both the representation and process and protocol. It might suit us to use tables, spreadsheets, documents, JSON, YAML, and so on. Graphs, networks, even just key value stores, ledgers, log files, all of these are potential data representations. And then thinking about scales, some changes are slow, some are fast. For example, a city grows rather slowly. New buildings are added quite slowly, but a drone moves very quickly, or an autonomous vehicle moves very quickly. So to form a narrative about the world, to reason about it, we need to follow and make changes to data in the model at different scales in space and time in order to make sense of these things. Slow things tend to be more predictable than fast things. This makes our view of the environment fundamentally non-deterministic, because we can't predict everything, and we have to deal with the unexpected. Now, in all of this, autonomy insulates us from some of the variables, so we naturally prefer to keep the parts independent or modular, autonomous. But here is the problem today. Although our uses for information technology have expanded enormously, our data modeling techniques have been very slow to adapt. You all recognize this kind of relational database model in the picture. These classic data models developed for IT were designed for a closed, protected, and deterministic world with immutable characteristics, unchanging characteristics. These databases like SQL, SQL, spend a lot of time modeling things where we have to search through all the things and then join together searches in order to model processes, because they're designed to record the attributes of things, devices, entities, instead of designing processes, which are the really active agents. So by modeling objects instead of things, we typically have a poor fit for mobile and data-rich processes in the modern world. But what I want to claim is that this means we need to start thinking more about how we arrange the data pipelines or the circuitry that connects together these agents so that they can be initially autonomous but can still share on a need-to-know basis to deliver information in ways like supply chains instead of using these gigantic search and join operations from centralized databases. And this is how we can deliver reliable intent and how agents can focus on their intent. Recently, we've made a few improvements here. There are new kinds of database today, like ledgers, even blockchain, spreadsheets, documents, graph databases. This image in the slide is a graph database, and you can see that it looks like a journey or a story, a map, a living data structure that grows with the process it represents. So these look a lot more like the processes they represent because you can add links and data to the points. And these points can be either real or virtual, and therefore we can create this data model that looks exactly like the process we're trying to represent. Every model has some kind of space and some kind of time, whether the space is a location in physical, geographical space-time, or if it's a functional piece of data representing a record or an event. So if we think of the internet, for example, the locations are not really, the IP addresses are not really the interesting thing about it, but the processes that make it work are the interesting part. We have slow processes of gathering information about places and routing, how things are connected together. And then we have the need to transport data rapidly from location to location by name, from Mark to Sally, from one IP address to another IP address. So we have scaled processes, a hierarchy of slow and fast processes, routing to transport. And so space and time, again, at different scales, are the important aspects. We have two options for trying to model processes in either real or virtual data spaces. One way is to be quantitative, using numbers and distances in this kind of grid approach, which we all learn at school, this Euclidean space coordinate system view. The other is to use qualitative models or names or attributes to identify the function of an object. So in the diagram you see a little treasure map where somebody starts in the location and then we say, go to the big tree, then go down the hill to the bottom of the hill and look in the hole in the ground and you'll find some treasure. So here, instead of having numbers, coordinates, and distances, we have landmarks that we identify using sensory capabilities. If we think about a hotel, we number the rooms in a hotel because they're all fairly similar. But if we think about a shopping mall, which is a functional thing where things are very different, we give the names to shops, or we base the identifiers on what they sell, so that we can identify what's going on. So we might number streets in a city in order to know where we are. Fifth Avenue is after 4th Avenue, before 6th Avenue. But we also want to use signs for the functions of buildings so that we know where to go to find the things that we need. An autonomous visitor then can just move around the space, detecting these landmark signals and adapting to the process instead of having to search a gigantic database and use search and join to create a picture. So it eliminates a lot of the information that agents need to know. A grid provides order and a sense of distance and navigation, but for contextual searching, we prefer to think about the places as landmarks. Autonomous systems are efficient here because they don't need to remember the whole grid. Yeah? They only need to have cognitive or sensory capabilities. So if space-time information were coordinated centrally by shared grids, a lot of information about the agents would have to be contained by a central controller. It would be quite inefficient in terms of time and energy. Landmarks are a direct semantic view of the world. And if any of you know about neuroscience, brains, you know that we have two kinds of cells in our brains to remember these two methods. We have grid cells for measuring distances and place cells for remembering the identity of locations. Okay, now let's look at how to design that fully distributed world in which locations and times are the database themselves. And agents moving around this database are the query operations. Semantics and dynamics can all be understood using promise theory. Promise theory is a graph-based representation, quite detailed, to approaching the modeling of space and time, or processes that connect together from locations connected by relationships. So we can use this in fault finding, we can use it as a form of space and time. In promise theory, everything is an agent. We can collect together agents as superagents to form groups. The way we do it is by joining them with bindings. And bindings are formed from agents that offer things and agents that choose to accept things that are offered. We can therefore use these joinings, these bindings, to form processes with direction by overlapping the needs and concerns of these agents. And then the way we arrange these agents and their promises form a set of boundary conditions. So promise theory describes a world of autonomous agents. They all start initially without any promises. And then as we add the promises to offer something or accept something, perhaps with conditions attached, we're able to distinguish the actions of different agents and make functional circuitry. We create circuits between these agents. We distinguish between push-based push-based impositions, where agents throw things at each other unpredictably. We distinguish that from more predictable promises, where agents have already agreed that certain transactions will happen in an orderly way. And that allows us to manage expectations. So promises give us a form of modeling, which is a bit like differential equations, only for graphs, where we set boundary conditions or the dependencies between agents, and then we look at the patterns of interaction between them in order to describe the dynamics and the semantics. Now, making agents aware of their context allows them to make local decisions. And we do this by promising to observe the environment around us. If we look at the right-hand side of this image, we see the world described as a series of levels in terms of information technology. At the top or at the edge, we can think of the active agents in an environment. And each individual agent here is looking at the world in its own way with its own information. Underneath, we create a kind of infrastructure to connect them together in a graph using the promises that they make to one another. And these promises may change over time a little bit, but they collect together groups that work together as a super agent. So the scales have both dynamic and semantic parts, order and function, and we organize them by scale. On a small spatial scale, we have the edge interactions at the top, and then centralized functions form connective layer underneath, where agents collaborate on a larger scale. This also applies in time, not just space. So over time, an agent can learn patterns of behavior, so on a short time scale, single events, but by grouping together events on a larger time scale, can create coarser events or slower trends. And on the left-hand side, we see process patterns learned by user interactions by observing a service. This is how we might include machine learning or even human learning into a system. Agents can then adapt their promises to these demands and different characteristics. So at each level, there are independent processes involving agents at certain scale. And when promises are kept regularly, patterns form. And these patterns form statistical invariant knowledge that can be observed and learned and passed on to other agents by signaling through the environment itself. SIFAKIS has showed some different possible strategies for these autonomous system characterizations. I think you know this paper. The semantic spacetime model shows us why and when to use these different strategies, whether they are more fixed programmatic ideas or adaptive algorithmic ideas, learning processes, or rigid predefined processes. If we equip agents with memory, then we can make them memory processes and they can adapt. Whereas if we give them no memory, they can't remember anything, then they become effectively Markov processes like billiards or ping pong. You don't know what's going to happen. You simply have to react in real time to impositions from outside. And this can be quite unpredictable, non-deterministic. So the goal then is to make space-time work for us rather than work against us. Promise theory predicts that there are 4 kinds of relationship between these agents that we need to think about. They may have many different names, but they're essentially 4 types. And these are what we need to understand causality, whether it's a real system or a virtual system. You see in this slide the 4 types. They basically represent space and time and information over space and time, and then a sense of distance. So whether, for example, a drone is part of a city, is inside a city or outside a city, or inside a region or outside a region, whether a room is inside a building or outside a building, whether a building is part of an organization or part of a district, is a building part of a city. This inside or outside concept is a way to understand how to generalize ideas. And then we have time, which is essentially sequence. So does this event precede another event? Does it come before? Is causality taken care of? This causes that. This depends on that. This happened after that. And then each of these locations can also express certain information, services, properties, and so on. So we can design and evolve these relationships as we advertise our properties and learn the attributes of other agents nearby. When agents interact, they can learn from one another and then use this to form a graphical representation, both locally around each agent, individually, autonomously, but then also share some aspects centrally. So this brings us back to the key question, which is what is the deeper role of autonomy here? We now have a way to construct a space-time compatible functional design from the bottom up by thinking about the cooperation of autonomous parts, each agent with its own timeline and its own resources. We can choose between centralization and decentralization as a scaling issue. What promise theory tells us is that centralization has mainly a functional purpose. It's not very good at dynamical scaling, but it's very good at calibrating standard behavior. So having a single central point of comparison is the way to avoid differences from diverging and becoming unpredictable and causing problems with relativity of agents, differences, and consensus. So let's be clear that the goal of autonomy and autonomous agent networks is not to create a kind of artificially intelligent organism that can think for itself, but rather to give sensible encapsulation to the processes and be smarter about the way in which these constrained processes can serve human needs, human decisions. We can take inspiration from brains and the intelligence that we see in animals and the environment around us, but basically we want to maintain autonomous control just in a hands-off way. Well, we've used this approach before. We have examples of systems that use these approaches today. CF Engine was probably the first. This was my work in the 90s. Still exists. Kubernetes has adopted these similar kinds of adaptive, autonomous responses to environmental concerns, but in a virtual way. In the virtual space of a cloud, agents can be created and destroyed, connected together, rewired as different forms of circuitry. Microservices are a design pattern associated with this kind of organization. And of course, going back to network function virtualization in the 2000s, which is widely used in 5G and 6G design, then these are ways of representing things in a service-oriented view. So there's a weak implementation of the idea in many of these technologies today. And each of these localized agents basically express these four types of promises: inside, outside, before and after, service functions, offer, receiving, and so on. Earlier, I mentioned data pipelines are going to be important. So this, as soon as we start connecting agents together, we have to say, what will the circuitry look like when we connect them? This paper about Koalja is something I wrote a few years ago, explaining how to connect using semantic spacetime. So once we have these smart autonomous locations and agents, we can go a step further than the models by adding follows relations inside and outside. And then we have this data circuitry. A few years ago, we built this prototype using Kubernetes called Koalja. So what we see from thinking about the function and semantics is that every adaptive process becomes a collection of smart data pipelines formed from essentially autonomous agents. And we can choose raw data, and we can choose to make the data smart by adding semantics so that the agents can adapt and process information adaptively. Today, we still don't do this very well because the technologies are designed for old-fashioned systems with these old-fashioned databases, and they don't take into account the big scaling picture or the big semantic picture. Suppose we look ahead to the next decade. What might the infrastructure look like for supporting this kind of system? We need to create scalable, order-preserving trails of data in a simple way. And the problem we face today is that there's no suitable infrastructure for this. There are a lot of open source projects. Everyone can put them together in their own way. So everyone ends up with a different system, and it all becomes a bit of a mess. There's no interoperability. But in terms of promises in space-time, we can already see how to make this work. What we want is something much more like content delivery networks, a generic platform that can service the entire industry in a very generic way. And again, by using these space-time processes from edge to center to aggregate, forming essentially a cone of a causality cone, we can generate agent rings of cooperation that can collect together signals and provide a platform for scaled cooperation. And if you want to read more about this, we've started implementing this together with a colleague in Hungary. We have a platform, a prototype, which deals with some of these difficult issues that are represented in the CAP conjecture, the so-called CAP theorem. So by building a containment hierarchy of sampling processes from edge to center, we can take into account all of these space-time ideas. So let me summarize really quickly. Promise theory is a network algebra for describing space and time. Agents express space-time ideas in the promises they make to one another, and this allows us to build these scaled cognitive loops, these red arrows in the picture. Agents learning from one another and sharing together. We can build a general infrastructure to support this, starting with autonomous agents and then working together to aggregate a cone of causality. Like all big transformations, there's an important human element to this, a social element. It takes time for engineers to think about problems, to adopt new technologies and so on. So this involves some social processes too. But the future of smart spaces is really waiting for this global platform to support autonomy and data sovereignty at scale, so that we can link up data into these smart supply chains or data pipelines, collecting local contextual information over arbitrary regions and building from that a unified semantic spacetime. So let me stop there and I'll take some questions.